Can you hear me now? Testing one, two, three. Yay! Oh my goodness. Okay, so we're 12 minutes into the stream. Um, do we go back to the beginning or do we continue from where we are? I'm gonna let you guys decide. Back to the top. Okay, that is perfectly fine. I'm gonna redo my intro and everything. Um, my name is Hunter. I am a pre-med post-bac student at Portland State University, and this is content review for principles of biology students. Um, this is probably my favorite quarter. We are kind of going back to what we covered in the fall with microbio and looking at DNA and sort of as the molecule of inheritance and how this is going to affect populations, right? So we were looking at uh, microbio cells, right, in the winter or in the fall rather. And in the winter, we were looking at cells forming tissues, forming organ systems, forming individuals. And now we're looking at individual to individual interactions writ large in populations. So I really, really like this one because it's kind of bringing everything all together. Um, Admin things, live streams will be at 4 on Thursdays. No attendance is taken. You are eligible for extra credit though, and to get that extra credit, you need to submit these worksheets for completion uh, by Friday evening, and that is in this other document that I had pulled up. Here we go. So all this information should be available to you in the Google Drive. That link should have gone out to you in an email. Um, any questions about that from those of you here in the chat? Now is your time. And if you're watching this in the future, you can find it on the PSU Learning Center YouTube channel. That is a perfectly okay way to engage. In an ideal world, y'all will have taken a look at these worksheets ahead of time and filled out the things that you know and come with questions. If that's not realistic for you, I totally understand. I was definitely one of those students who just sat down with this worksheet and watched the stream and filled things out as we went, and it was good kind of review for me. And the tutor sort of talking through their thought process was really helpful for me. So whatever you need to get out of this is fine. If you want those extra credit points, make sure you submit something um, by the deadline. Okay, back to the top. So we're talking about evolution. We're talking about mechanisms of evolution, or evolutionary processes rather. And we're actually going to first talk about a theorem that is about populations not experiencing evolution. This is our kind of our baseline or equilibrium. So if evolution can be defined as a change in gene or more appropriately allele frequencies, is it conversely true that a population not undergoing evolution should maintain a stable gene frequency from generation to generation? And this was the question that scientists Hardy and Weinberg answered independently. So this first exercise is just definitions filling in some blanks. Um, 1A is population, an interbreeding group of individuals of the same species. There are many theories of species or speciation that we'll get into later in the term, but one of them, principally, is the ability of individuals in a population to reproduce being a defining trait, right? If you have a population that is suddenly separated and their genetic makeup changes sufficiently that they can no longer reproduce with um, new members of that population, then that would be a new distinct species, many would argue. B, we have gene pool. All of the alleles contained in the gametes, that is the sex cells, egg and sperm, of all the individuals in the population. Egg and sperm specifically in eukaryotes like us, like humans. In the population. Genetic drift is evolution, again defined as a change in allele frequencies that occurs specifically in small populations as a result of chance events. So if you are among a population of mice that live on a tropical island and a wave comes and wipes out half of the mice population, that is going to have a significant effect on the genetic makeup of the mice on that island, right? So that is an example of genetic drift. It may actually be a better example of bottleneck effect, which is like a big cataclysm, but I digress. The Hardy-Weinberg theorem. The Hardy-Weinberg theorem states that in a population that is not evolving, the allele frequencies and genotype frequencies remain constant from one generation to another. And this is part of these make up the fundamental assumptions that need to be true or that we are making in order to apply the Hardy-Weinberg equation, which we're going to get into in a second. And these assumptions are in your textbook. You can find the page numbers here on the worksheet. First one, A, there are no random allele frequency changes that would affect the gene in question. B, there's no net migration of individuals into or out of the population. Net, of course, is total. So if two individuals leave and two individuals come back to participate in mating in that population, there's no net change. Similarly, there's no net mutation. There's no net mutations. That is, the forward and backward mutation rates for alleles are the same. Big A turns into little a at the same rate that little a turns into big A. D, mating is at random for the trait or genes in question. So having a gene or not does not change the likelihood that you are going to pass on that gene, which leads directly into the final assumption, which is there is no selection. Offspring from all possible matings for the trait or gene are equally likely to survive. That is, those last two assumptions in particular, um, uh, how did I say this just a moment ago when my microphone was turned off? Um, yeah, if a trait offers differential reproductive success, then evolution must be occurring, right? Or is likely occurring. No, must be. Yeah, if it's differential reproductive success is by definition an evolutionary evidence of evolution. Okay, so the Hardy-Weinberg proof. This is where we are now applying the language of math to these observations. So consider a gene that has only two alleles, big R, which is dominant, and little r, which is recessive. The sum total of all big R plus all little r alleles equals all of the alleles at this gene locus, or 100% of all of the alleles for that gene. Okay. So let P equal the percentage or probability of all of the dominant big R alleles in the population. P, dominant alleles. And Q is the percentage or probability of all of the recessive little r alleles in the population. Therefore, if all big R plus all little r alleles equal 100% of the alleles, then P plus Q equals 1. P plus Q equals 1. And this allows you to now create, to write an inequality, where if you know the number of P alleles in a population, you can mathematically determine the number of Q alleles. And usually this actually happens the other way around, because if there are, we'll get into this in a second, but if you can count, we're going to do this as an exercise. You can determine the frequency of a recessive allele by the number of homozygous recessive individuals that are expressing that recessive trait, and then applying this equation, which you'll see in a second. Frequencies are stated as percentages, so 50% would be 0.5. Assume that 50% of the alleles for fur coat in a population of mice are big B, black, and 50% are little b, brown. The fur color gene is autosomal. Autosomal is an important word to know and understand. This just means that it's not sex-linked. It means that male and female reproducing individuals are going to pass on these genes at the same rate. And the cropping is weird on this. always, but we'll do what we can. Yeah, there's only one of these missing. What percentage of the gametes in the females alone carry the B allele? Again, because this is not a sex-linked trait, this is going to be 50%. What percentage of the gametes in the females alone carries the little b allele? Again, 50%. And it doesn't matter what big B and little b represent in terms of the trait. We're just looking at the individual alleles and are they dominant or recessive. The same is going to be for males carrying big B and little b alleles. Now, the one that is cropped out here asks, given the preceding case and all the Hardy-Weinberg assumptions, calculate the probabilities of the three possible genotypes, big R, big R, big R, and little r, occurring in all possible combinations of eggs and sperm for the population. And they've already done the first one here for us. So this is your classic Punnett square, right? It would behoove you to get used to drawing these. Um, and I'm reading back above just to make sure that we are dealing with heterozygous individuals. 50% of the alleles for fur color in a population of mice are big B black and little b brown. Yes, okay. So this is our 50%. Cool. Big R goes with big R. And I'm actually going to stick to. I see a message in the chat here. Why is autosomal important? It's an important vocab term to know and understand because it contrasts to sex-linked traits, which we'll get into in a second, which is going to change this equation quite a bit. So autosomal just means that you get to do the example, run the example as I'm about to show you. So big R goes with big R, forms big R, and big R with little r forms big R, little r. And this is a heterozygote. Hetero meaning more than one, zygote, these are the chromosomes that we're talking about, or the alleles rather. Same thing here, we have little r and big R, and little r with little r. This individual is homozygous recessive for that little r trait. Heterozygous, adjective. And this one here is homozygous dominant for that R allele. Okay. Because the offspring types, oh, well, now we can kind of calculate our frequencies. And you can do this just by counting, right? We have 4 squares represented here, right? Our homozygous dominant occurs in one of those 4 squares, so that's 25% of the time. Our heterozygotes, which is what the question was about, is in 2 out of those 4 squares, so 50% of the time. And little r, homozygous recessive, occurs 25% of the time. Do our little math check. 25 plus 50 plus 25 does in fact equal 100%. So all of our individuals are accounted for, or all of our possible genotypes are accounted for. Okay. Because all of the offspring types represent all possible genotypes for this gene, it follows that, I'm going to rewrite this so it's all on the same line. P squared plus 2PQ PQ plus Q squared equals 1 or 100%. This is the Hardy-Weinberg equation. And just to do the exercise to kind of help you visualize this, so RR is P squared. Little r is Q squared. That's our recessive. And let's do red. Our heterozygous individuals are represented by the quantity 2pq. So remember when earlier we were talking about how the quantity p plus q represents 100% of the alleles that are present. If we know these, or if we know q squared, which we're always going to know because if it's homozygous recessive, it's going to show up, we can determine all of these other variables that are present in the population as long as evolution is not occurring. Now, use your understanding of the Hardy-Weinberg proof and theorem to answer the following questions. According to the Hardy-Weinberg theorem, p plus q equals 1 and p squared plus 2pq plus q squared equals 1. What does each of these formulas mean and how are the formulas derived? I've kind of already answered this, but we can hash it out again. So p, all of the dominant alleles, plus q, all of the recessive alleles, equals 1. All dominant and all recessive alleles account for 100% of alleles for that gene. And then we have p squared plus 2pq plus q squared equals 1. And this means that all homozygous dominant plus, excuse me, yeah, I want to go in order here, plus all come on, all homozygous dominant plus heterozygous plus homozygous recessive equals 100% of individuals with a given gene. Is everyone able to hear me just fine when I'm talking and writing at the same time? I've had problems with that in previous terms. I'm going to color code things while I'm waiting to hear back from folks. Okay, fantastic. Audio is working good. Okay, moving on. Assume a population is in Hardy-Weinberg equilibrium for a given genetic autosomal trait. There's that word again. What proportion of individuals in the population is heterozygous for the gene if the frequency of the recessive allele is 1%? We should remember that p plus q equals 1. That's 100% of them. We're given the value of q, the frequency of the recessive allele. So p plus 0.01, that's 1 in 100, equals 1. Subtract that from both sides. Yeah. So the frequency of P then is 1 minus the frequency of Q, gives us 99 and 100, or 99%. Let's make it a little bit more complicated. Make sure you can read that. About one child in 2500 is born with phenylketonuria, an inability to metabolize the amino acid phenylalanine. This is a pretty big deal. It means you can't eat things like eggs, fish, milk, grains, uh, dairy. There's a lot of things that you can't eat. Um, this is known to be a recessive autosomal trait. So just to review what recessive autosomal means, uh, this means that you need to be homozygous recessive, little r, um, for this characteristic to be expressed. Um, if you have the gene for phenylketonuria, but do not experience that illness, you may be a carrier, right? But you won't experience any symptoms. Your offspring may have to worry about it though. And we're cropped again. If the population is in Hardy-Weinberg equilibrium for this trait, what is the frequency of the phenylketonuria allele? So let's go ahead and assume that P, big P, is the normal allele, and little p is the phenyl ketonuria allele. And we are not given the frequency of little p. We are given the frequency of homozygous recessive individuals, which is different. That means we need to use that larger equation, which is, well, we'll get there in a second. We're told the value of q squared. So remember, p squared plus 2pq equals, sorry, plus q squared equals 1. We were given the value of q squared, which is 1 in 2500, right? We can simply take the square root of that to get q equals 0.02 or 2% if you were to put that into your calculator. So the frequency of Q, the frequency of the allele for phenylketonuria, is in 2% of the population, or rather 2% of the alleles in the population. All right. What proportion of the population constitutes carriers for the phenylketonuria allele? That is, what proportion is heterozygous? This is asking what 2pq is. No, it's not. Apologies. So we figured out what the value of q is. Now we go back here. P equals 1 minus q equals 98%. I was right the first time. 2pq. We needed to first solve for p. 2pq equals 2 times the quantity 0.98 times 0.02 equals 392. Yeah. So 3.9% of the population are carriers for this condition, but will never experience symptoms. All right. Question 4. Any questions so far? Okay. In purebred Holstein cattle, about one calf in 100 is spotted red rather than black. The trait is autosomal, and red is recessive to black. Red is recessive. Autosomal. Don't need to worry about different rates of inheritance. So what is the frequency of red alleles in the population? Well, we're told that 1 in 100 has the red spots. That is our q squared value. We're also told that it's recessive, so we know it's q and not p. Square root of 100 is 10, so q equals 1 in 10, or 10%. So 10% is the frequency of red alleles in the population, not the frequency of red spotted cows. That is 1%. What is the frequency of black homozygous cattle in the population? So remember, this is going to be different than the number of black cows because you can have heterozygous, big R, little r cows that are totally black because the black gene is dominant. So this is asking the value of p squared. And this is different from how I would solve it, but 1 minus q equals p. So p squared equals the quantity 1 minus q squared. We know the value of q, which is 1 in 10. So p squared is 81 in 100. C, what is the frequency of black heterozygous cattle in the population? This is asking for that quantity 2pq. So we had 2 times our q allele was 1 in 10, and our p allele was 9 in 10? I don't think that's right. Yes, it is. 9 in 10. 9 times 2 is 18. It's 100. So 18 in 100 is the frequency of black heterozygous cattle. Yeah, where did the 1 minus q squared come from? So I had a feeling that was going to happen. P plus q equals 1. We rearrange that so that p equals 1 minus q. If we're solving for p squared, we can simply square that entire quantity. Does that make sense? It wasn't at all clear to me at first either because I do not speak the language of math particularly fluently. I'm trying to get better at it. Um, this is one of the many ways that you can use one equation to solve for variables in the other, basically. I hope that answers your question. Um, I said I would do it differently because I would first have to solve it this way, kind of like we did up above, just because I know how to do it reliably that way. So the real answer here is find a way that works for you and stick with it. Um, Doing it the way that I've shown here allows you to, it's just faster, right? Um, it's allowing you to solve multiple steps in the same line, basically. Yeah, but because I'm not fluent yet, I'm not conjugating these equations, if you'll forgive the pun. Um, so I do it a little bit more stepwise, if that makes sense. Yeah. Okay. Question 5. Assume that the probability of a sex-linked gene not autosomal, if I can spell autosomal. Assume the probability of a sex-linked gene for color blindness is Q equals 0.09. So it's recessive and the allele is present 9% of the time. Uh, the docs, including this worksheet, should have been emailed to you in a link. Or, yeah, you should have the link in an email. And if not, email your professor about it. Um, okay. The probability of a sex-linked gene for color blindness is Q equals 0.09, and the probability for the normal allele is P equals 0.91, which we could figure out mathematically knowing Q. This means that the probability of X chromosomes carrying the color blindness allele is 0.09, and the probability of X chromosomes carrying the normal allele is 0.91. What is the probability of having a colorblind male in the population? Well, we're kind of the question is answered in the question. I'm gonna stick to black here. The reason that it is 0.9% is because in females that have two X chromosomes, you're getting genetic input from both parents. But in XY individuals, you're just getting genetic input for this trait on from one parent, um, from mom. And so if the probability of having that gene, if the frequency of that allele on the X chromosome is 0.9%, it will show up 0.9% of the time in males. So what is the probability of a colorblind female? So again, it's different because you're getting um, genetic input from both parents. And so this, in this case, we go straight back to that earlier Hardy-Weinberg equation, or 0.09 squared, which is 8 in 1,000. So very, very, very rare by comparison. Um, for males with this trait, you're going to see it almost 10% of the time. And for females with this trait, you're going to see it, 8 in thousands, 8 in 1,000. So This is to show the mathematical basis for why it's so much more rare to see um, females with a sex-linked trait expressed. Right? All right. The ear tuft allele in chickens is autosomal. Is autosomal. That's not what I clicked on. And produces feathered skin projections near the ear on each side of the head. This gene is dominant and is lethal in the homozygous state. In other words, homozygous dominant embryos do not hatch from the egg. Assume that in a population of 6,000 chickens, 2,000 have no ear tufts and 4,000 have ear tufts. What are the frequencies of the normal versus ear tuft alleles in the population? So this is asking for the values of P and Q. Um, since the homozygous dominant individuals aren't hatching, we don't know directly what the frequency is, but we do know that in a population of 6,000 chickens, 2,000 have no ear tufts. Hang on. Sorry, my screen is doing something weird. There we go. Okay. Yeah, I don't. Okay. Basically, we are told what the quantity of 2PQ is, and that was 4,000 out of 6,000. Is that right? I'm dissatisfied with how the answer key explains this. Yeah, 66%, 0.6 repeating, so 67% is 2PQ. This is the heterozygotes. Um, how do we want to? Yeah, so that's 2/3. Another third, 2,000 and 6,000, is Q squared, have no ear tufts. And so the remaining 33% must be P squared. 33% plus 66% would be, is that right? No, it's 2/3. I'm thinking about this completely wrong. I'm so sorry, guys. Hmm. Okay, because we don't know how many eggs did not hatch or how many of these contained homozygous tufted chickens. We need to calculate the allele frequencies by assigning alleles to the existing population. I'm just gonna. So this is the number of tufted alleles, and this is the number of normal alleles. We have 4,000 tufted and 2,000 normal. So we know we have 4,000 tufted. So 4,000 total available. Allele frequencies, 4,000. Where are they getting that? 6,000 available. 12. Okay. There's 12,000 total alleles available. Yeah. Okay. That's where they got that. Now I understand. Okay. Each of the tufted the tufted individuals is carrying this dominant allele for that trait. There are 4,000 of these individuals present in a population of 6,000. In 6,000, we have two alleles per individual, so 12,000 total alleles. 4,000 out of 12,000 is 33%. That's where I went wrong. By contrast, these are our homozygous recessive individuals who do not have tufted ears. That's 8,000. 8,000 little t alleles. 8,000 divided by 12,000 is 0.66 or 66%. So I had it backwards. It's not to do with the number of individuals, it's the number of alleles. So this is an important change in thinking and a trap that I fell right into. So I hope this is a little bit clearer. So if these are in Hardy-Weinberg equilibrium, we would expect subsequent generations we would get something like this. Equals 2/3 Q equals 2/3. Then we multiply across basically. So 1/3 times 1/3 equals 1 in 9. All of these individuals will not hatch. Here's our heterozygote, big T, little t. It's going to be 2 in 9, big T, little t, 2 in 9. And little t will not have tufts. We have 4 in 9. Whew. Okay. I'm glad I could make that mistake on the first day for you guys and see me work through that. Um, Teaching this does not mean we get it perfect every time. So, yeah, this is part of that process. What are the frequencies of the normal versus ear tufted alleles in the population? There you go. So this was your frequencies up top. And this is what the next generation would look like. Okay. How can one determine whether or not a population is in Hardy-Weinberg equilibrium? What factors need to be considered? We talked about forces of evolution, right? Can't be present, no migration, etc. So to determine whether a population is in Hardy-Weinberg equilibrium, you need to be able to calculate the number of individuals in the population that are homozygous versus heterozygous for the alleles. And because recessive traits won't be expressed in heterozygotes, excuse me, because those traits won't be expressed in heterozygotes, homozygous recessive individuals are the easiest ones to count. So if you know the frequencies of each genotype, you can then calculate the allele frequencies, as we did in question 6. So I suppose I should do some writing. Um, so to determine if a population is in Hardy-Weinberg equilibrium, you must be able to calculate the number of individuals in the population that are homozygous versus heterozygous for the alleles. If you know the frequency of each genotype, you can calculate the allele frequencies, as we did in question 6. And given the allele frequencies, you can calculate the genotype frequencies that would be expected if the population were in Hardy-Weinberg equilibrium. Then compare those values to the known values. So given allele frequency, you can calculate expected versus real um, expected versus real frequencies. Yeah. In reality, this is really difficult because if alleles showed dominance, or if alleles show dominance, it's hard to distinguish the homozygous dominance from the heterozygotes. So as a result, we tend to look for the frequency of those homozygous recessive phenotypes in a population. If this remains relatively constant from one generation to the next, we use it as evidence to assume that the population is in Hardy-Weinberg equilibrium. So the key factor there is from if these rates remain the same from generation to generation, then Hardy-Weinberg equilibrium is likely, uh, the population is likely in equilibrium. All right, last question, and I know we're out of time. Is it possible for a population's genotype frequencies to change from one generation to the next, but for its gene or allele frequencies to remain constant, and explain by providing an example? Um, I won't get into the mathematical basis for this, but the answer is yes, and the example is non-random mating. For example, um, non-random mating, i.e. inbreeding in a population of mice. So the alleles present will remain the same, but the genotype frequencies will change. And you will, well, basically this will result in an even distribution of um, homozygotes and heterozygotes rather than differential representation that would usually be. And you get a lot more expression of deleterious traits that way. That is all I have for you. Thank you all for your attention, for bringing my attention to the fact that my microphone wasn't working properly. If we can get all of these out of the way in the first week, subsequent weeks will go a lot smoother. Um, so thank you guys for your patience. If I look tired, it's because I am. I'm in the middle of moving. So next week, my environment might look a little bit different, but Goose, my puppy, will still hopefully be in the background, taking a nap. Yeah, I'm talking about you. Um, so email me if you have any questions. I can be found at hlea@pdx.edu. And again, you can find the recordings on the PSU Learning Center YouTube channel. Don't forget to turn in your worksheets by Friday. I will see you all next week.